Good afternoon, everyone. Thank you for giving me an opportunity to present my work. I'm Sachin Joshi, second year PhD student at Laboratory Hubert Curien. So the title of my presentation is Joint Estimation of Bead Parameters and Geometrical Aberration Estimation in Inline Digital Holographic Microscopy. So here beads are the silica microsquares which we used in microscopy for for calibration purposes. So the main aim of this study was the estimation of aberrations in inline holographic setup for microscopic phase objects. Further, to study the effects of aberrations on the parameters estimation of microscopic objects. So these are the contents of the slide. First, I give a brief introduction about the subject, about digital holography. Then I talk about inline holographic setup that we have set up in the lab, and about reconstructions of the acquired holograms, then about the results we got, and then I conclude the presentation. So talking about microscopy, so it's difficult to visualize phase objects, which are transparent objects, using a traditional microscopy, as so we have to stain the samples. But if we use digital holography, so we can retrieve the phase of the samples. So there is no need of staining. The principle of digital holography is shown in the figure. We just need a coherent source of illumination, and we record an out of focus image of the object that we have, and we get a digital hologram. And in the schematic, okay, in this schematic, we can also use other optics. After that, suppose if we want to use microscopy, we can use microscope objectives and further include more optics. So after the acquisition of hologram, then we have to reconstruct the hologram. So on figure B, I have shown the inline holographic setup that we have set up in the lab. Now I'll explain this setup. So here is the schematic representation of the setup that we have. So we have a coherent illumination source, that is lasers, and it passes through the optics and goes through the sample. For the sample, we have to record a defocused image, which are shown here. So it is the in focus image, and it is the hologram, which is the defocus image that we will reconstruct afterwards. And the zoom in of what happens near the microscope objective is shown here. So we have a cover slip here, and immersion medium, and calibration objects. Further, the light goes through the microscope objective, and objective have here it's shown different aberration correction collars. So these aberration correction collars, they compensate for the thickness of this cover slip. So if the compensation of the cover slip thickness is not correct, then it will induce spherical aberrations in the images. So now, so we can acquire the holograms. Now talking about the reconstructions of the holograms. So basically, after the acquisition of holograms, the next step is reconstruction of the hologram. So we use inverse problem approach for reconstructions. And so it's basically a fitting problem. So we fit a model to the experimental measurements. Our experimental measurements are the hologram. So for the simple objects, simple spherical objects, we have we use the Lorentz B model for the estimation of parameters. So we can estimate the location of the particle, XYZ coordinates, and the size of the particle, and the refractive index of the particle. So here in the figure is shown the reconstruction process. So we have the experimental hologram this, and we fit the model, which depends on the XYZ Rn coordinates. And then we minimize the error and find the best results. And the parameters we get are the best results. So this model is simple model in which the aberration effects are not taken into account. So only 5 parameters are estimated. So to add the aberration effects of the optical setup, we use a Zernike polynomial sequence. So it is a sequence that can be used to model aberrations of the optical system. So the aberration coefficients 1, 2, 3, and 5 are not taken into account. and we estimate the rest of the aberration coefficients. So total there are like 11 aberration coefficients. So to add the effect of this into the model, so we simply convolve the aberrated pupil function, which depends on the aberration coefficients, and the me model. We simply convolve them, and now the model can possibly estimate the aberrations too. So for this model, we have like estimation of total 16 parameters, which comprises of 11 aberration coefficients and 5 simple like XYZ location and radius of the object and refractive index of the object. So talking about the experiments now, so we reconstructed like 250 beats for each aberration correction color setting. And afterwards, for comparison, we also reconstructed the beads without taking aberrations into account. So talking about the results, so this is how the spherical aberration coefficient varies in the field of view. Here it's shown X and Y field of view. And we can see that it's there about 0 for the aberration color setting 0.17, which is supposed to be the best aberration color setting, because the measured cover slip thickness was around 170 microns. So we get a quite very nice result for the spherical aberration characterization. And talking about all the other aberrations except for spherical aberrations, so we can see that they vary in the field. And these are the RMS wavefront errors. So these are all the aberration coefficients which are non-radial. Further talking about the comparison between the model corrected for aberrations and model which was not corrected for aberrations. The above it's shown the uncorrected model of aberrations. So we see the Z estimation for each aberration correction color setting. So the point clouds are separated from each other in this graph. In this graph. But with the model with the aberration correction, we see the point clouds are quite superimposed over each other. So the Z estimation are quite better for the correction with aberration. But R estimation and N estimation still show a little bias, which are shown a little here. So these are the results for the comparison between the model for correction and not correction. So finally, concluding my presentation, so we were able to jointly estimate the beat parameters and aberration coefficient for several beats in inline holographic setup. And we saw that the reconstructions improved for the estimation of propagation distance of the particles that were assumed. And characterization of aberrations are quite important for the microscopy setup if we are analyzing microscopic objects, because it can affect the analysis. And further, we can also extend this study for different illumination angles and also characterize as if we provide illumination to the tilt, so it would result in some aberrations and we can characterize them. So thank you for your attention.